And let's talk now about the linear uniformly accelerated motion. And actually, when we have a velocity that increases, we will see different cases like this one. So we have an object with a positive velocity moving to the positive direction, and we have an acceleration also positive. What does that mean? Let's have an example here. Let's say that the acceleration is 4 meters per second squared. That means that the velocity changes by 4. So if the initial velocity is 0, after a second it will be 4, after another second it will be 8, and so forth. Now the position, let's consider that the initial position is 0. When the velocity changes from 0 to 4, in that second, it does a distance of 2 meters. So after a second, the position will be at 2. Now, from 4 to 8, then the next second, the velocity changes from 4 to 8, and at that second, the object does a distance of 6 meters. That means that it will be 8 meters away. How do we know that? How can we prove it? So we have the velocity changing by 4 every second. The distance traveled in the first second is this area, which is half base times height, half times base, which is 1 second, times height, which is 4. So this will be 2 meters. So the displacement for the first second is 2 meters. For the first 2 seconds, the displacement is half base, which is 2 seconds, times height, which is 8. So the displacement for the first 2 seconds, a total of 2 seconds, will be half times 2 times 8. So we can see that it's 8 meters. So in our table, our position changed from 0. In 1 second it went to 2, and in another second it went to 8. Now, there's another way to find these values from the table without even using the graph. Okay, so we said that the velocity started from 0 and it changed by 4 every second. So the velocity in the first second changed from 0 to 4. All right? Now, if the velocity was 4 the whole time, the distance traveled would be 4 meters, would be this rectangle. But now it changes from 0 to 4. That means that the distance traveled, the triangle, which shows the displacement traveled, is exactly the half of the displacement that we would have if it had a constant velocity. So again, just by finding these two values, by seeing this and finding the half, the average is 2, gives me the displacement. Exactly the same we have between these two values. So here, the velocity changes in the second, the velocity changes from 4 to 8. If instead of having a velocity that changes from 4 to 8, if instead we had a velocity of 6 the whole time, this area and this area are exactly the same. So just the second, it did this distance, which actually is the same, if instead of having a change in speed from a gradual speed change in the velocity from 4 to 8, if we had a constant velocity of 6, we would have done the same. So finding the average between these two values, 6, it gives me the increase at that second. So actually, this can be used the whole time. And it can not only be used when the object speeds up, it can be used when it slows down. So let's say that I'm telling you that, let me read through this. So let's say that I'm telling you that a car speeds up from 0 to, I don't know, from 0 to 10 in 5 seconds, right? So let's say that it increases from 0 to 10 in 5 seconds. If it had the speed of 10 the whole time, the velocity of 10 the whole time of 5 seconds, it would do 50 meters. Now that it speeds up from 0 to 10, it does exactly the half, 25. And you can tell that the triangle is exactly the half from the rectangle. The same thing, we have the same thing when the object will slow down. Let's say that my car slows down from 10 to 0 in 5 seconds, right? So if it had the constant velocity of 10 for the whole time of 5 seconds, it would do 50 meters. But now it slows down to 0. So the distance traveled, the displacement traveled, is exactly the half, 25. I know that. I don't need to do the math. I can see the answer, and if the answer is exactly the half, I know it's correct. This saves me and you a lot of time. Now, going back to the notes, we can see that the graph of the position time graph will be a parabola. We don't care for the negative part, we care only for the positive part, because negative time means past. So it is a parabola. How can we tell? How can we know? In this simple case where there's no initial velocity and we start from initial position 0, we can see that the term half acceleration times squared gives us the position. Half times 4 equals 2. This is 2. So at time 1, 1 squared gives us a 2. 2 squared, 4 times 2, 8. If I go to the third second, my velocity would change by 4, therefore it will be 12. If I do it as I said, the average between 8 and 12 is 10, so this will go to 18. But again, this works because it's half times 4 times 3 squared, which is 18. So this is the formula that gives us the position when the initial position is 0 and the initial velocity is 0. So we see that the position depends on time squared. That is why the position time graph is a parabola. Now, if I had a position time squared, that would be a straight line, right? A straight line that the slope would be half acceleration. The slope of this is half acceleration. Now we definitely understand that just because the velocity is a linear graph, it has the form y equals mx plus b, where y is the velocity now, x is the time axis now, the slope is the acceleration, and the y-intercept is the initial velocity. In the case of position, the full formula is this. Because the position depends on the initial position, on the distance made by the initial velocity plus any additional, should use displacement the whole time. Plus the displacement made because of the acceleration changing the velocity. These are the full equations that we have and we're going to use. So here we have objects A, B, C, D. We see that A slows down, B and D speed up, but B has a higher acceleration, higher slope, while C has a constant velocity. It does uniform motion. Again, talking about the velocity time graph, the slope gives us the acceleration, the area gives us the displacement, while the position time graph, the slope gives us the velocity, and you see that I have no math here because we're not going to do that. You're going to see it when you do Physics C. The same thing happens when everything goes to the negative direction. When acceleration is -4, for example, velocity increases in the negative direction to the left. Okay, now for this example, I considered that my object was already at a distance, let's say 8 meters to the right, but by moving to the left, it reaches the origin. And of course, if I could see the next second, I would see that its position would become negative because it would continue going to the left. So in this case, we see that the velocity time graph is a linear graph with a negative slope, and the position will be a parabola, but the parabola upside down because of the fact that the acceleration is negative, and I don't want to talk about it because I would need to talk about math, and if you make me, I will do. So let's stop here because this video is very big. We will talk about decelerated motion in the next video.